All right, so for the vector-valued function that we were looking at before, we're now going to find the unit tangent vector. So the first thing that we should do is actually calculate the derivative. That's not difficult to do. All we have to do is differentiate each component separately. And when we do this, let me just remind you that what does this r prime of t give us? Well, if we plug in a particular t value, this is going to be a vector that's parallel to the tangent line to the curve. So it'll be a tangent vector, but the problem is it may not be a unit tangent vector. Remember, a unit vector is a vector of magnitude 1, and we can actually compute this magnitude, and we'll see very quickly that this is not a unit vector. So to compute the magnitude of a vector, we square each component and add them together. So square the first one, 25 sine squared of 5t. Second one is just 25 cosine squared of 5t. And the last one is 4t squared. We can use our nice trig identity. Sine squared plus cosine squared is equal to 1. You can see very explicitly where that comes up if we factor a 25 out of this, these first two terms. And there's this 4t squared left over. So this actually winds up giving me 25 plus 4t squared under the square root. And that most certainly is not 1. So we can see that this r prime is not actually a unit vector. But there's a very easy way to find a vector in the correct direction, i.e. parallel to the tangent lines to the curve, by just finding a unit vector the same way that we always find unit vectors. So my unit tangent vector here, r prime of t is in the correct direction. All we have to do is divide it by its magnitude to obtain a unit vector and write down the result. So not a particularly difficult process. R prime of t is going to give me a vector in the correct direction, but it's not necessarily a unit vector. But all we really have to do is just find its magnitude and divide r prime by its magnitude to get that unit vector in the right direction. All right, so for the second part of this problem, to emphasize a point, let's actually look at how the magnitude of r prime of t is changing and how the magnitude of the unit tangent vector is changing. So for this first one, this is a good study in making sure that you understand what notation means here. What this process is telling me to do is find r prime, which we already did, find the magnitude, which we already did, then take a derivative. So we found here that this magnitude was just 25 plus 4t squared, all raised to the 1/2. So all we actually have to do is take a derivative of this, and that's really just an exercise in Calc 1, right? So here we'll have to use the chain rule. Just take a second and rewrite the square root as a 1/2 power. Chain rule tells us to multiply by 1/2, lower the power by 1, then multiply by the derivative of the inside, which is just 8t. So what we're going to get here is a 4t all over root 25 plus 4t squared. And so it's not a hard calculation, but I want you to notice here that this magnitude is clearly changing. It clearly depends on what t value we plug in. So if we're asking how do the tangent vectors given by r prime of t change, there are two ways that they're going to change. The magnitude's going to change, and also the actual direction can change as well. So that's a very different story, however, if we're going to look at the unit tangent vector. So for this last part, when we're taking the derivative of the magnitude of the unit tangent vector, this is actually a really easy question because we know what the magnitude of the unit tangent vector should be. So we know that for any t here, the magnitude of this guy should be equal to 1. It'll take a second after the video just to verify that, but if this magnitude is always 1, what happens when we take a derivative? Well, the derivative of this is the derivative of 1, and that gives me 0. So the nice thing is if we're looking at the unit tangent vector, if that's non-zero, the only thing that can change about it is its direction, not its magnitude. Okay, so just to emphasize the point that magnitude of the unit tangent vector is 1, I do want to compute it. So just as a little note to finish off the problem, we found in part 1 of this that our unit tangent vector looks like this. And so we'll actually very explicitly compute the magnitude of it. So that's not a bad thing to get in the habit of. If that line in the last little video looked a little bit weird, if you didn't know why the magnitude of this should be 1, you can always compute this yourself. Just pause the video and give it a try. I'll do it here though explicitly. So when we calculate this magnitude, it's going to be a little bit more annoying to write out right now, but we'll do it in gory detail just to make sure. So this first component looks like this, and we have to square it. All right, so this little function of 1 over root 25 plus 4t squared on the outside, this would be distributed to each component. So the second component here is going to be 5 times cosine of 5t. And we're going to divide all of that by that root 25 plus 4t squared. Square it. And then the last one will be a 2t over root of 25 plus 4t squared. Clean that up. OK. So running out of a little bit of space there, but it's not too bad. So when we square all of this, what happens? Well, we square the numerator, we get a 25 sine squared of 5t. Square the denominator, we just get a 25 plus 4t squared. Square the numerator, get a 25 cosine squared 5t. Square the denominator, get a 25 plus 4t squared. And last but not least, we'll square the numerator, 4t squared. Square the denominator, 25 plus 4t squared. So that looks pretty algebraically messy, but we can now combine all of these fractions, and we'll see something very similar to what we saw before. So when we combine the numerator, we can also factor out this 25 from the first two terms, and we'll get that familiar-looking Pythagorean trig identity, sine squared plus cosine squared. We'll have a 4t squared left over. And in the bottom here, we're going to have a 25 plus 4t squared. Well, now hopefully you can see exactly what's going to happen. That sine squared plus cosine squared is going to be 1. So on the top, we're going to have a 25 plus 4t squared. In the bottom, we're going to have a 25 plus 4t squared. And so at the end of the day, we do indeed get exactly what we hoped, 1. So take a moment, just make sure that you understand these calculations. But it's not too bad. A little bit algebraically messy, but whenever we actually find the unit tangent vector, we are constructing it in a way so this magnitude is always 1. So that's not something that you really ever have to check. It's something that's going to be a consequence of how we find the unit tangent vector.